The 1950s should have been American railroading's triumphant decade. Instead, it became a graveyard of failed experiments, engineering disasters, and locomotives so problematic that crews openly celebrated their retirement. As diesel power threatened to make steam obsolete, desperate railroads and builders created machines that combined the worst features of both technologies while adding entirely new categories of failure. These weren't just bad locomotives, they were expensive catastrophes that accelerated the very extinction they were designed to prevent. Pennsylvania Railroad's T1 class limped into the 1950s, carrying the burden of unfulfilled promises and mechanical chaos. Raymond Loewy's streamlined masterpiece looked like the future when 50 production units rolled out between 1945 and 1946, but appearance couldn't disguise fundamental engineering mistakes that no amount of tweaking could fix. The 4-4-4-4 duplex arrangement split driving wheels into two sets, each powered by separate cylinders. This promised smooth power delivery and reduced hammer blow damage to track. What it actually delivered was violent wheel slip that terrified passengers and destroyed components with depressing regularity. The problem was adhesion. Dividing drive wheels meant each set carried only half the locomotive's weight for traction. At starting, engines slipped violently, spinning wheels while trains remained stationary. Engineers learned to ease throttles open with surgical precision, but any slight miscalculation sent drivers into wheel slip that could damage valve gear and coupling rods. More dangerous still, the T1 slipped at speed. Imagine pulling a 12-car passenger train at 75 miles per hour when front drivers suddenly lose traction. The locomotive lurched forward as slipping drivers caught again, creating a rhythmic surging that passengers described as dancing across the rails. Engineers fought constantly to maintain smooth running, adjusting throttle and valve settings almost continuously. Franklin poppet valve gear added another layer of complexity. More precise than traditional Walschaerts gear, it buried components in locations mechanics couldn't reach without major disassembly. A single valve adjustment required hours of work. Multiply that across 50 locomotives running daily service and maintenance costs exploded beyond any projection. The valve gear's intricate linkages wore rapidly under the stress of wheel slip. Components broke frequently, and replacements were expensive custom castings. By 1950, Pennsylvania Railroad was spending more maintaining T1s than operating conventional steam. Roller bearings throughout the valve gear and running gear should have reduced friction and maintenance. Instead, they created new problems. These bearings required precise alignment and constant lubrication. Any misalignment caused rapid wear and failure. The streamlined shrouding that made T1 so beautiful created its own nightmares. Mechanics needed to remove entire sections of shrouding to access routine maintenance points. What took minutes on a conventional locomotive consumed hours on a T1. During heavy maintenance, shops spent days removing and reinstalling cosmetic coverings just to reach critical components. PRR began removing shrouding in 1948, but this created its own problems. Partially de-skirted T1s looked terrible, undermining the prestige they were supposed to project. Water consumption proved astronomical. The large firebox and high steaming capacity meant T1s drank water faster than tender capacity allowed. On long runs, they required more frequent water stops than older locomotives they replaced, negating any time savings from higher speeds. Firemen struggled to maintain steam pressure during hard running. The firebox demanded constant attention and perfect coal distribution. Any lapse meant pressure dropped and performance suffered. By 1952, dieselization was accelerating and PRR management faced a choice. Spend millions debugging T1s or invest in proven diesel technology. By 1953, every T1 was retired or stored. Most were scrapped immediately. Not one was preserved. PRR's embarrassment was so complete, they wanted no reminders of this expensive failure. Around the same time, Chesapeake and Ohio discovered their M1 turbine experiment had been an expensive mistake from the beginning. 3 of these monsters were built by Baldwin Westinghouse between 1947 and 1948, combining coal-fired steam boilers with turbine drives and electric motors. Coal dust proved to be the M1's nemesis. The fine particles infiltrated the traction motors constantly, grinding away at windings and commutators. Crews reported motors burning out on nearly every run. The sealed motors proved impossible to keep sealed. Once inside, the abrasive particles destroyed expensive components with ruthless efficiency. The boiler controls proved temperamental, requiring constant adjustment to maintain proper steam pressure for turbine operation. Unlike reciprocating engines that tolerate pressure variations, turbines demand consistent steam conditions. The turbine itself operated at such high temperatures that metallurgy of the era couldn't handle sustained operation. Turbine blades developed cracks after relatively few operating hours. When C&O finally retired all 3 M1s in 1956, they'd accumulated only about 150,000 miles each, a fraction of what conventional steam locomotives achieved. The M1 proved that combining steam and electric technologies just added the problems of both while solving issues of neither. Pennsylvania Railroad's Q2 class represented what happened when engineers learned just enough from previous failures to create new categories of disaster. 26 of these 4464 behemoths rolled out between 1944 and 1945, and they consumed water like they were trying to drain the entire Susquehanna River. Q2s required water stops far more frequently than conventional locomotives pulling identical trains. The 16-wheel tender carried 25,000 gallons, enormous by any standard, yet Q2s could drain it in under 100 miles of hard running. Making matters worse, the boiler leaked chronically. The automatic wheel slip control system seemed brilliant until it actually had to work. When failing, which happened often, the locomotives slipped violently at speed, destroying drive gear and valve components. The firebox arrangement created another problem nobody anticipated. Designed for maximum steaming capacity, it demanded perfect coal distribution and constant firing attention. Firemen described it as the most physically demanding locomotive they'd ever worked. By 1951, every Q2 was retired or stored. The Q2's brief career proved that raw power meant nothing if the locomotive consumed resources faster than it could generate revenue. While Pennsylvania struggled with their duplex disasters, Norfolk and Western learned that steam turbines belonged in power plants, not on rails. Their sole turbine locomotive, nicknamed John Henry, proved grimly appropriate since it worked itself to death trying to compete with diesel. Baldwin Westinghouse delivered this 176-foot monster in 1954. The fundamental problem was the same as every turbine locomotive. Turbines achieve efficiency at constant high speeds, but perform terribly during acceleration, deceleration, or slow-speed operation. During yard switching, the locomotive consumed fuel at catastrophic rates while producing minimal useful work. On the main line, acceleration from stops consumed so much steam that pressure dropped dangerously. Maintenance costs exceeded the worst projections. By 1957, severe turbine damage ended regular operation. N&W scrapped the locomotive in 1959. John Henry had logged perhaps 100,000 miles in 5 years, less than many conventional locomotives achieved in a single year. Union Pacific's gas turbine experiment started more successfully than most, but by the 1950s, their fleet of G-TEL units was revealing problems that would ultimately doom the entire concept. The problem was fuel. Gas turbines can burn almost anything, so UP decided to use Bunker C, the cheapest, dirtiest fuel oil available. At room temperature, it's nearly solid. To make it flow, UP had to heat it to nearly 200 degrees Fahrenheit. The fuel heating system failed constantly. Any interruption meant fuel solidified in lines and filters, stopping the locomotive completely. Bunker C contains high levels of sulfur, sodium, and vanadium. These contaminants attacked turbine blades, causing rapid erosion and corrosion. The exhaust from burning Bunker C was environmentally catastrophic. Black smoke belched from gas turbines in quantities that made steam locomotives look clean. Noise proved equally problematic. Gas turbines scream at frequencies that carry for miles. Communities near UP lines lobbied for restrictions on when and where turbines could operate. By 1958, UP began calculating total operating costs and discovered they were spending more per ton-mile with turbines than with diesel-electric locomotives. UP began quietly retiring gas turbines in the late 1950s. By 1970, every gas turbine was scrapped. While UP struggled with turbines, Baldwin was desperately trying to prove they could build competitive diesel locomotives. Their Centipede design became a rolling advertisement for why Baldwin would ultimately fail in the diesel market. These massive 6,000 horsepower double units looked impressive with 12 axles and sleek Raymond Loewy styling. They performed terribly. The fundamental problem was that Baldwin tried to design diesel locomotives like they were steam engines. Accessibility was terrible because Baldwin seemed convinced that components needed to be buried deep within the car body where mechanics couldn't reach them without major disassembly. The electrical systems proved equally problematic. Control systems failed frequently. Traction, motors burned out regularly. Reliability was so poor that railroads running Baldwin diesels kept spare units available just to replace failures. The prime movers were Baldwin's own design, and they were terrible. Engine failures plagued the entire Centipede fleet. Pistons cracked, cylinder heads warped, fuel systems leaked. Oil consumption was astronomical. By the mid-1950s, railroads were retiring Centipedes as fast as they could justify. Pennsylvania railroads scrapped their entire Centipede fleet by 1962. Not one was preserved. Baldwin ceased locomotive production entirely by 1956, killed partly by disasters like the Centipede that destroyed customer confidence. Fairbanks Morse entered the diesel market with excellent marine engine technology, but their opposed piston design proved fundamentally unsuited for railroad service. The opposed piston engine seemed brilliant. 2 pistons in each cylinder moving toward each other from opposite ends eliminated cylinder heads, reducing parts count. In marine service, where engines run at constant speeds, opposed piston designs work fine. Railroads aren't marine service. Piston failures plagued FM locomotives from the beginning. The opposed piston design required perfect synchronization between the 2 pistons in each cylinder. Any variance meant pistons collided, destroying both pistons, the cylinder liner, and often damaging the crankshafts. Crankshaft failures were equally common. The opposed piston design used 2 crankshafts per engine, connected by gears. These crankshafts experienced tremendous stress, and FM's metallurgy wasn't up to the task. The supercharger system added another layer of complexity and failure. When superchargers failed, engine power dropped by more than half. By the late 1950s, most railroads had concluded FM diesels were more trouble than they were worth. FM exited the locomotive market in 1958, their reputation destroyed by unreliable products. Lima Hamilton thought they could compete in the diesel market despite having no real diesel experience. Their diesel switchers and road switchers built in the early 1950s proved that ambition without expertise creates disasters. Engine failures plagued every LH diesel from day one. The Hamilton engines weren't designed for the sustained high-load operation that railroads demanded. Cylinder heads cracked, pistons failed, crankshafts broke, cooling systems proved inadequate, and engines overheated constantly. The electrical components were sourced from whoever offered the cheapest price, resulting in a mix of incompatible systems that fought each other. Reliability was so poor that railroads took delivery of brand new LH locomotives and immediately assigned them to storage, keeping them as spare parts sources for the units that were actually running. By 1954, LH had effectively exited the locomotive market. Not a single Lima Hamilton diesel was preserved. LH diesels were so bad that railroads literally paid to make them go away faster. American locomotive companies' high horsepower passenger diesels looked competitive on paper, but proved maintenance nightmares in service. Their PA models, introduced in the late 1940s and built into the early 1950s, combined impressive styling with mechanical complexity that destroyed Alco's reputation. The 244 engine that powered PAs produced good horsepower but consumed oil at rates that shocked railroad maintenance departments. 1 quart per mile was common. 2 quarts per mile wasn't unusual. Railroads found themselves adding hundreds of gallons of oil between major terminals, a cost they hadn't budgeted and couldn't justify. The oil consumption created multiple problems beyond just expense. Oil dripped from everywhere, creating slippery walking surfaces and fire hazards. Station platforms became coated with oil slicks that caused passengers to slip and fall. Lawsuits followed. The oil consumption also indicated deeper engine problems that Alco never adequately solved. Engine reliability proved equally problematic. The 244 suffered chronic cylinder liner problems. The liners wore rapidly and allowed combustion gases to blow past pistons into the crankcase. This contaminated the oil with acids and carbon, accelerating wear throughout the engine. Pistons cracked from thermal stress and detonation. Cylinder heads developed cracks that let combustion gases escape, reducing power and efficiency. Turbochargers failed regularly. The turbocharger bearings couldn't handle the sustained high-speed operation that passenger service demanded. When turbochargers failed, power dropped by more than 30%. Fuel injectors malfunctioned constantly, causing rough running and black smoke. Any given PA was likely to be operating on fewer than all 16 cylinders at any time. Electrical systems added to the misery. Alco used General Electric electrical components, generally superior to Westinghouse equipment Baldwin used, but GE's generators and traction motors weren't optimized for the high speeds and sustained operation that passenger service demanded. Generator failures left PAs dead on the road, stranding passengers and disrupting schedules. Traction motor failures were common, particularly on units assigned to heavy trains or mountainous routes. Cooling fan motors burned out regularly, leaving engines without adequate cooling. Passenger railroads prided themselves on reliability and on-time performance. PAs threatened both. Santa Fe found their PA fleet spending more time in shops than on trains. Maintenance departments struggled to keep enough PAs operational to meet scheduled assignments. New Haven's PAs were so unreliable that they kept older, less powerful locomotives available as backups, negating any efficiency gains the PAs supposedly provided. Delaware and Hudson bought used PAs cheaply after other railroads retired them, discovered why they were cheap, and regretted the purchase immediately. The streamlined car body that made PAs, beautiful created access problems that made maintenance expensive and time-consuming. Engine access required removing large body panels secured with dozens of fasteners. Mechanics needed to remove multiple panels just to reach routine maintenance points. Major repairs required practically removing the entire car body shell. What should have been simple tasks consumed entire shifts. Passenger service demanded cleanliness that PAs couldn't maintain. Oil consumption meant oil dripped everywhere, coating walkways, steps, and platforms with slippery residue. Railroads received complaints from passengers who slipped on oil-coated station platforms. Some passengers sued, adding legal costs to the PA's already problematic economics. Cleaning PAs became a constant battle that maintenance departments couldn't win. By the late 1950s, most railroads concluded PAs were more trouble than they were worth. Santa Fe began replacing them with EMDE units as quickly as delivery schedules allowed. Engine life was measured in hundreds of hours instead of the thousands diesel engines achieved. Transmission problems plagued every gasoline switcher. Plymouth used automotive-style transmissions that couldn't handle the shock loads from coupling. Gears stripped, clutches burned out. Rebuild intervals were absurdly short. The mechanical drive system meant these locomotives had no ability to modulate tractive effort smoothly. Clutch engagement was abrupt and violent. Industrial railroads discovered Plymouth switches were cheap to buy, but expensive to own. By the late 1950s, Plymouth had shifted to diesel power, tacitly admitting gasoline power was unsuitable. Steam diesel hybrids seemed like logical transition technology, but every attempt created locomotives with problems from both power sources and advantages of neither. Baldwin's experimental units from the early 1950s demonstrated why mixing technologies creates complications rather than solutions. Baldwin combined diesel engines with steam generators for passenger car heating. The concept solved a real problem, but created far worse ones. Maintaining two separate power systems multiplied maintenance requirements. Mechanics needed diesel engine expertise and boiler expertise. Parts inventories doubled. Baldwin discovered they'd discovered locomotives that required twice the maintenance while being available for revenue service half the time. Passenger railroads tested steam diesel hybrids briefly, concluded they were terrible ideas, and returned to conventional diesel locomotives. The steam diesel hybrid proved that solving one problem by creating two worse problems isn't engineering progress. Several railroads experimented with radio-controlled locomotives in the 1950s, and early systems proved spectacularly unreliable. Remote control locomotives in switching service could eliminate the need for engineers riding the locomotive, improving efficiency and visibility. What actually happened was locomotives running away uncontrolled while operators frantically mashed transmit buttons, hoping for response. The fundamental problem was radio reliability. 1950s radio technology wasn't robust enough for railroad operating environments. Control signals failed to transmit through buildings. Steel structures reflected and absorbed, and radio waves. Electrical interference jammed frequencies. Safety systems were primitive or non-existent. If radio contact was lost, the locomotive continued executing its last command until collision or derailment forced a stop. Railroads concluded radio control added complexity without adequate reliability. By the late 1950s, most radio control installations were removed. The technology would eventually mature, but 1950s implementations proved the concept was ahead of available technology. Narrow-gauge railroads struggled through the 1950s with aging equipment that should have been replaced decades earlier, but couldn't be replaced because narrow-gauge equipment wasn't being manufactured. The Denver and Rio Grande Western's K36 class, Mikados, represented relatively modern narrow-gauge steam, built in 1925. Yet by the 1950s, they were worn out and increasingly troublesome. Narrow-gauge operation itself was economically doomed, but railroads couldn't afford immediate conversion to standard, or gauge. Boilers were approaching their pressure vessel life limits by 1950. Frames showed cracks from decades of service. Running gear wore beyond economical repair limits. Everything was worn out simultaneously, but replacing components on narrow-gauge locomotives was expensive because nothing was standard. The D&R GW struggled through the 1950s operating narrow-gauge service with equipment that grew steadily worse until traffic declined enough to justify abandoning entire routes. The narrow-gauge operations proved that sometimes technology reaches a dead end, where continued operation is impossible, but alternatives are unaffordable. Coal-burning steam locomotives lingered on some railroads through the entire 1950s, and their problems multiplied as the decade progressed. Norfolk and Western operated the last significant fleet of modern steam locomotives in America, and by the late 1950s, even they were discovering that steam's day had definitively passed. Their Class A and Class J locomotives worked well. The problem was that everything around them was changing. Coal quality declined. Water treatment became more difficult. The skilled labor force that maintained and operated steam locomotives was retiring or leaving for better opportunities. Shops designed for steam locomotive maintenance were closing or converting to diesel service. Replacement parts became impossible to obtain as suppliers exited the market. The regulatory environment changed as environmental awareness increased. These factors accumulated until even railroads committed to steam concluded dieselization was inevitable. Norfolk and Western completed dieselization by 1960. Steam's death came not from a single failure, but from 1,000 small complications that made continued operation impractical. Some locomotives failed not from mechanical problems, but from being solutions to problems that no longer existed. Pennsylvania Railroad's L6 electric switches, built in small numbers in the early 1950s, represented massive locomotives optimized for yard switching in electrified territories that were about to disappear. These 185-ton behemoths seemed logical when built, but PRR's electrified freight operations were already shrinking as traffic patterns changed. The L6 entered service just as the infrastructure justifying their existence was being dismantled. Electric locomotives could only operate where catenary existed. As PRR de-electrified freight lines, the L6s became stranded assets. They sat idle while diesel switches handled work the L6s were built to perform. Crews disliked operating L6 because they were crude and uncomfortable compared to modern diesel switches. By the late 1950s, PRR was parking L6 and using diesels even in electrified territories. The L6 were retired in the early 1960s, having operated barely a decade. They proved that building specialized equipment for infrastructure that's being abandoned creates expensive white elephants. Multiple unit diesel operations created problems nobody anticipated fully until fleets grew large. Control systems from different builder eras weren't always compatible. When incompatible units were combined, control systems fought each other. Loading became uneven. Dynamic brake coordination proved especially problematic. Some units applied full braking, while others provided minimal braking. Multiple unit connections themselves proved less reliable than manufacturers claimed. Electrical connections corroded, creating intermittent failures. Cable damage was common. Cold weather created additional problems. Control system relays became sluggish. These problems accumulated until railroads developed experience-based rules about which locomotives could safely work together. But this knowledge was gained through expensive failures throughout the 1950s. Rail diesel cars seemed like ideal solutions for branch line passenger service, combining self-propulsion with passenger accommodations in single units. Budd, Pullman Standard, and others built hundreds of RDCs in the 1950s. Many were problematic from the beginning. Diesel engines mounted under passenger compartments created noise and vibration that passengers found unacceptable. The engine compartments made maintenance access terrible. Mechanics had to crawl into cramped spaces beneath the floor to work on engines and transmissions. Transmission problems plagued early RDCs. The mechanical drivetrains weren't robust enough for railroad service. Cooling systems proved inadequate. Climate control was problematic. The lightweight construction that made RDCs economical to operate also made them vulnerable to damage. Several fatal accidents involving RDCs led to concerns about passenger safety in lightweight vehicles. Railroads operating RDCs accepted their problems because alternatives were worse. But they were never good options, just economical compromises that railroads tolerated until abandoning passenger service entirely. These 20 locomotives from the 1950s represent American railroading at its most desperate and experimental. Faced with extinction from highway competition and airline growth, railroads gambled on technologies that promised salvation but delivered failure. Steam builders created ever more complex locomotives trying to match diesel efficiency, while adding problems conventional steam never had. Diesel builders rushed products to market before fully developing reliability. Experimental technologies proved decades ahead of supporting infrastructure. The result was a decade of expensive mistakes that accelerated rather than prevented the very changes railroads feared. Nobody wants these locomotives back because they represented everything wrong with 1950s railroading. Desperation masquerading as innovation, complexity substituting for development, solutions creating worse problems than they solved. The lessons they taught were expensive but clear. Sometimes technology reaches its end, not through dramatic failure, but through accumulating compromises that make continued operation impractical, regardless of performance. These locomotives taught American railroads that lesson brutally and expensively. Don't forget to subscribe so you don't miss future updates. Here's another video I've specially selected for you. See you next time.